Hello. In this video we will learn about the tension force that strings, wires, and cables produce. To begin our discussion, let's start with an example. Here we have a block of mass m suspended from the ceiling by a string. Gravity is pulling down on the block with a force of mg. However, you don't expect the block to fall. After all, it is being held up by the string. That means the string must be producing some upward force that cancels the downward gravity. We call this force the tension force. But what is the source of this tension force, and how can we predict its behavior? There is one main assumption that we will always make when dealing with strings or wires. We will assume that they do not stretch at all. Now, you might think that you've seen wires and strings stretch, which is true, but if you have a strong wire or cable, a typical amount of force won't cause it to stretch any noticeable amount. So this is the key assumption. Returning to our example, if the block were to fall, then the string would have to stretch. The only other alternative is that the ceiling would fall with the block, so that the string wouldn't have to change length. But we are going to assume that the ceiling stays put. Since we know the string can't stretch and the ceiling won't move, that means the block can't move either. Therefore, the string must be exerting a tension force that is equal and opposite to the gravity force. So the entire trick of the tension force is as follows. A string or wire will produce whatever tension force is required to keep it from stretching. I also should point out that we will usually assume that the string or wire has no mass, or at the least, its mass is insignificant compared to the mass of the strings it is attached to. So let's try to apply our newfound understanding of tension to another example. Here we have two blocks that are attached to each other by a string, and one of the blocks is being pulled by someone on the right. If that force pulling on M1 was the only force involved, then M1 would accelerate while M2 would not. If that happened, then the string would have to stretch, since M1 would be moving while M2 would not. Again, that is not possible. In fact, for the string to not stretch, M1 and M2 must have the same acceleration. For this to happen, the string must be exerting a tension on M2 to pull it along. Because of action-reaction, that tension force needs to have an equal and opposite partner, which acts on M1. Now, notice that I didn't draw any forces acting on the string itself. This is because the string is massless, and a force cannot act on a massless object. If it could, then F equals ma wouldn't make much sense. Just think about that for a second. If mass were zero, then force has to be zero. Rather, the massless string transmits the force through itself, and applies that force to the objects attached on each end. Each object feels the same tension force, but in the opposite direction. Let's quickly work out the acceleration of these two masses, which we already said has to be the same. So let's start with the F equals ma equation of m1. We have m1 times a equals the applied force pulling to the right minus the tension force pulling to the left. Now let's do the equation for m2. We simply have m2 times a equals t, pulling to the right. Go ahead and solve for the acceleration yourself. Finally, let's look at one of the most important applications of strings and tension, the pulley. On the left we have a mass m2 sitting on a frictionless surface. On the right we have a mass m1 hanging by a string. The two masses are connected by a string, but first that string winds around a pulley. In real life, a pulley is usually a circular object that can spin. The idea is that you can wrap the string or cord around the pulley, and the pulley will spin as the string passes through it. This way the string can change direction and won't experience much friction as it passes through the pulley, since the pulley turns, so it doesn't have to scrape along it. For our purposes, we will assume that there is no friction from the pulley and that the pulley has no mass, so it takes no effort to spin it. When we work with pulleys, we only need to consider two simple things. The pulley redirects the string, and the forces are still transmitted perfectly through the string. That means that the pulley also redirects the force, which can be a very useful tool. Let's look at our example here and work out the acceleration. Our hanging block is experiencing a force of m1 times g downward. However, if it were to accelerate and the other block did not, then the string would stretch. Therefore, the two blocks must have the same acceleration. More precisely, they have the same magnitude of acceleration, but the directions are clearly going to be different. Block 1 will move downward, and block 2 will move rightward. On the other hand, you can work with your own system, where the only direction you consider is along the string. In that case, they are indeed moving in the same direction. Then you just have to choose one direction to be your positive, and one to be the negative. I will choose this to be our convention. Again, in order to get the same acceleration, m2 must be pulled by the string with a tension force of t. By action-reaction, m1 is also pulled with a force of t. in the opposite direction along the rope. So let us write our equations. For m1 we have that m1 times a equals mg minus t. Now I made mg positive because that is pointing in the direction that we decided should be positive, while t is pointing in the direction we said should be negative. Next, m2 times a equals just the tension, which is positive. Go ahead, figure out what the acceleration is.